Hello, good morning. Today we are handling a continuation of what we started yesterday. Yesterday we started with quantitative data analysis, part 1. We handled correlation. Today we are handling quantitative data analysis, part 2, handling regression analysis. What is regression? We are starting with linear regression. Linear regression is a general method for estimating or describing the association between a continuous outcome variable, which is normally dependent, and the predictors, the y versus the x's. The predictors could be continuous, e.g. the weight, the height, the blood pressure, or it could be categorical, e.g. gender, sex, level of education, TB status, etc. Linear regression allows the researcher to estimate the magnitude, the strength, and the significance of the relationship between a continuous outcome and a predictor from a sample. It also helps the researcher to develop an equation to predict the outcome value given values of the predictors for observation, not in a sample. This is a simple linear regression model. This is how it looks like. We have the x-axis, where we have the x values. Normally, these are the independent variables. And then we have the y-axis, which is normally representing the dependent variables. And the linear regression model is basically a line of best fit that kind of is closest to the points that we saw yesterday in our scatter diagram. These points, a line that closest to the points, that best fits the points are scattered along that line, is the regression line. If you take a point, for example, x1 and a point y1, and you see the regression line given by the equation y equals beta 0 plus beta 1 x. That regression equation line, which is actually light green there, that regression equation line is composed of the value of y hat, which is the point where the line crosses the y value. So that point with a dot is the value of y hat, and the real value of the observed value, or the actual value of y, is the dot with black dot. The difference between the value of y hat, the observed value, and the real value is the error term. The error term. In research, what we observe may differ slightly from what is actual. So the difference between what we observe and the real value of that actual outcome is the error term. And the error term is also described there as y1 minus y hat. Okay, so that is a regression model drawn on the xy coordinate. And there is what we call a y-intercept, which is the beta 0 down there, where the green line cuts the y-axis. That is called the y-intercept. And so the equation which of that line is y equals beta 0 plus beta 1. So beta 1 is actually the slope of that line, and it is indicated there by beta 1. So in simple linear regression model is defined by the equation y equals beta 0 plus beta 1 x plus the error term, where beta 0 means the response when x equals 0. Okay? When there's no x at all, you can observe some changes in something. That is the y-intercept. Beta 1 equals the change in the mean response when x increases by 1 unit. So that is normally what we are interested in when we are doing regression analysis. What happens when the value of x increases by 1 unit? What do you observe? Okay, so that is what we are normally interested in regression analysis. When the independent variable increases by 1 unit, what happens to the dependent variable? That beta 1 is the most important variable in regression analysis. Now, the error term, or we call it sometimes disturbance term, represents the factors other than x that affect y. There are many things that can affect y. So if you can eliminate most of them, fine. But even if you try to eliminate them, you might never eliminate everything. So whatever you cannot eliminate that may cause a change in y, we call it error term. We call it error term. Because if you wanted, for example, to find out what causes people's income levels, so sometimes you say, oh, it is education. Sometimes you say it is the background. Sometimes you say that it is chance. Sometimes you say it is innovation. The person is very entrepreneurial. Sometimes you say it is and so on. There are many factors that cause people's income levels. But there are things that you might never eliminate or discover. So those ones are what we call error term. They cause an increase in income, but you have not put a finger on it. So how do we estimate this simple linear regression? We estimate the parameters using a formula, and those parameters are defined as follows. Beta 1 is basically equals to the summation of x times y minus n and the mean of xy, divided by the summation of x squared minus n times the mean of x squared. And beta 0 equals y mean of y plus beta 1 times the mean of x. So where x bar equals the mean of all the x values, y bar equals the mean of all the y values, and the summation xy is actually the summation of all the x multiplied by y values from 1 to n. And the summation of x squared is basically all the x squared summed together. Example. If we take an example of a CD4 count data, this is coming from public health, and CD4 count is basically something about the load, the virus load, the HIV virus load in somebody's blood is called CD4 count. So the question is there a non-zero effect of TB status at the point of initiation to ART on CD4 count at 6 months follow-up? So if you have TB, if you have also HIV, and you're starting on antiretroviral treatment, how does your CD4 count behave when you do follow-up every 6 months? So to answer this question, we test the hypothesis that the beta 1 is 0. There's no change in beta 1. When you start your antiretroviral treatment and you also have TV, that there will be no change in your CD4 count. But that is what we call the null hypothesis. The alternative hypothesis says there will be change, there will be difference. If you start treatment of ARV and then you also have TB, that you will, the difference in your CD count will be seen. The equation of the regression line relating to the estimated change in CD4 count given you have a particular age is given as follows. CD4 count equals to beta 0 plus beta 1 times your age. That is the regression equation for that, to find how age affects your CD4 count. The y-intercept is there given by beta 0, and that means that when the CD4 count for the patient, this is a CD4 count for a patient without TB. And beta 1 means the mean change in CD4 count per unit change in age. We continue. When this data can also be analyzed using Stata. There is a software called Stata that we can use to analyze quantitative data of this nature. So the regress command in Stata will perform the regression and give us the estimated slope, which is B1 or beta 1, and the intercept, which is beta 0. That one, you just open the statistical software known as Stata, and when you are there, you can give a command, namely regress. And the syntax, what you type there is regress y, then space. You normally start with an independent variable. You regress y on x. When you have done that and you click return, you will get your result. So we normally regress the dependent variable on the independent variable. So the independent variable is normally the predictor. Now, when you have done that, this is what your output will look like. This is what your output will look like, because you have regressed CD4 count on age. And so the results will be like, what is important here, of course, this model will bring all these results, but you will go down to the second last row you find here, CD4 count, and then you'll find the coefficient, the standard error, the t-value, the probability of t, and then the confidence interval, 95% confidence interval. The coefficient for age is minus 0.155, and then there's a constant. So you're trying to find how does age affect your CD4 count here. So the intercept always is the constant here in that output table, and the B1, the beta 1 is the slope. Is the slope that shows the value of the predictor. Eventually, what is important are those values that are marked with the arrows, the B0 and then the B1, or the beta 0 and the beta 1. But also up there, you'll see that we have circled adjusted R squared, which is 0.0033, and then the root mean squared error, which is 184.9. So this is a categorical predictor. This output shows a categorical predictor, and therefore the CD4 count vis-a-vis the TB, you see the coefficient is 0.19, negative 19.8, and the constant is 301.65. Standard error is given, the t-values are given, and the probability of t is given, and the confidence interval at 95 is. Then you go back to the adjusted r squared, and you find it is 0.009. These are very, very minimal impacts. TB, they are very, very minimal impacts because the adjusted R is very, very small. So that shows the rate at which Y or whatever Y increases when X changes. Very small indeed. So what are the regression assumptions? The true relationship between the response variable Y and the predictor variable X is linear. 2, the errors are normally distributed with zero mean and a constant standard deviation. And 3, the model errors are statistically independent. So that was a linear regression analysis. But we also have what we call multiple linear regression. The other one was simple linear regression. This is multiple linear regression. Simple linear regression, you have only one independent variable. In multiple linear regression, we have several independent variables, x1, x2, x3, x4, but one dependent variable, namely y. Example, we may want to look at the average change in the CD4 count in relation to sex while controlling for other variables like age and TB status at the time of initiating treatment. So here you have, we want to see how the CD4 count changes, but there are three other variables. There is sex, there is age, and there is TB status. How does all these three affect the CD4 count? So we may be interested in seeing how weight, for example, changes for babies with a unit increase in age while controlling for other factors like literacy levels of the mother, religion, and so on. So that's another example. We want to see how weight changes with a unit increase in weight, age, in the literacy level of the mother, region where they come from. So those three are the independent variables, while the dependent variable is weight. So those are multiple regression. Multiple regression. Multiple linear regression allows one to evaluate the association between an outcome and multiple, more than one predictors in a model. Age, weight, age, literacy, religion, region, and all those factors, including income level. Those are independent variables. They can all be simultaneously computed in a multiple linear regression. So we estimate the amount of the variation in outcome explained by the multiple predictors. So we investigate the interactions between the pairs of the predictors. And this is the model. The model is defined as follows. Y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, like that until beta p xp. Then you add the error term, where b0 is the y-intercept, b1, b2, b3, and so on are the parameters we estimate. Then x1, x2, x3, x4, and so on are the predictors in the model. And then E is the error term or the residual variability. So that is how we write a multiple linear regression model. Now, how do you test for significance of the overall model, or what we call the F-test? So the F-test tests whether any of the explanatory variables are associated with the response. The x's, so many x's, how do they associate with the response? So this tests the hypothesis. We start with the null hypothesis that beta 1 equals to beta 2 equals to beta 3, and so on. All the betas, all the parameters here, there is no difference. When you see as equals to 0 means there's no difference. So the weight of a child is not affected by any of those parameters, not affected by any of those variables. So we start with the null hypothesis. There will be no change in the weight regardless of all those factors. Then there's also what we call the alternative hypothesis, written as HA, which means that all the betas are not 0. So there is a change. There's a change in the parameters. So you have what we call the observable variance of F. F observed is equal to the mean square root over the mean square errors. And so we reject the null hypothesis if F observed is greater than F computed. And here is an example using the CD4 count. Let's look at the results we would get if the regressed CD4 count against sex alone. So you remember we were regressing CD4 count against sex. The results are down there where you find the coefficient of sex is 50.46. Then there's a constant of 261.54. There's standard error, there's the value of the t, the value of the probability of t, and then the intervals. Then we move on. The adjusted R square is still small, 0.0163. And you see the probability of t here is 0.00. And the root mean square is 179. So in this example, you find that if you want to see how the CD4 count will change in relation to sex while controlling for age, controlling for TB status, controlling for all other status, the model would look like this. CD4 count equals B0 or beta 0 plus beta 1 times sex plus beta 2 times age plus beta 3 times TB, so on and so on, plus the error term. So this means that change in CD4 count given a unit sex while controlling for the other predictors. So that is how you would compute how would CD4 count change if, depending on the sex of the person. But then all the other factors are kept constant. How would the CD4 count change? Now, to fit the multiple linear regression model using Stata, we use the regress command. Once again, you go to the syntax, you type regress, then you start with the dependent variable y, and then give space, then you type x1, x2, x3. x1 is age, x2 is TB status, x3 is sex, and so on and so on. So you type all those, and then you press enter command. So in this scenario, you define this is the output that you get from the multiple regression analysis using starter. Once again, you go down there. CD4 count is our dependent variable, and the independent variables are, you look at the coefficients, sex 66.1, age 0.76, TB is minus 9.36, and there is a constant. So there is a constant down there. So if you want, you can go on to look at the adjusted R squared. It's also 0.017. The root mean square is 183. So what are the assumptions here of the multiple linear regression? There is no collinearity or multicollinearity among the predictor variables. What does that mean? That two or more of the X variables are telling the same story, i.e., they contain the same information. Collinearity or multicollinearity means that the data is similar. If the data for X1 and the data for X2, data for age, data for TB status, data for sex are similar, if those things are similar, you'll find what we call collinearity. This one will be correlating with that one, the other one correlating with that one, that one correlating with that one. So when we have collinearity or multicollinearity, your results will not be predictable. It's not going to be reliable. So you make sure that the data, your data, are not collinear or multicollinear. So you test for those collinearity or multicollinearity when you do the alpha test. When you do the alpha test and you find alpha of 0.9 or 0.95, then you know that your variables are collinear, have collinearity or multicollinearity. That you have to do something about it. Otherwise, your results are not going to be reliable. So there's also what we call analysis of variance, which is a variation in X, the variation in Y that can be partitioned into two variations. There's what we call the explained variation and then the random variation. So ANOVA is about explaining the two portions of the regression. There is the total change is equal to the portion which is explained, and then there's that portion which is a random variation. Like we've said before, there are things that cause particular changes that we see. I was talking about income levels. How does one become rich? There are many factors that cause riches, but you can try to list all the factors that cause people to be rich, but you will not find all the factors. You can never know all the factors. So the factors that are not known are the so-called random factors. Those are the random variations. So those random variations, they are part of analysis of variance. So when you are looking at the variance that you observe, there is the explained variable and the random variable. So analysis of variance is composed of this. There's a model, which is the sum of the squares, there's a degree of freedom, there's a mean square root, and then there is the F value. There's also the error term, which is the SSE, and the degree of freedom is n minus p minus 1, and the mean square is SSE divided by n minus p minus 1. Then there's a total, which is the total observed variation, and the degree of freedom is n minus 1. 1.